Welcome to the lecture for Chapter 3. Chapter 3 is for discussion on theories of failures. This chapter requires the information that is gained from stress transformation because it will use the principal stress values in the analysis. The first part of this lecture is for discussion on theories related to failures of ductile materials. Now, in this chapter, the learning outcome is for everyone to understand the importance of theories of failure, able to identify when and where to use the theories, and able to analyze design problems using the most suitable theory of failure. The scope of study in this chapter will cover four main theories and one general knowledge theory. So we have maximum shear stress theory, or not commonly called Tresca, maximum distortion energy theory, or called von Mises, and maximum normal stress theory called Rankine, and Morse failure criterion. And the last one, Sand-Wiener's criterion, is rarely used nowadays, but we will discuss that later on at the end of the chapter. Why we need to know theories of failure? It is important for us to place an upper limit on the state of stress that defines the material's failure for design purposes. So normally we use this theory when we do sort of design from scratch a new product, or when we do design checking. So it checks the upper limit or the maximum value of stress that can be applied to a component or object. And then we look at two different types of materials. One is ductile material and the other one is brittle materials. Ductile materials normally fail by initiation of yielding. So normally we will use sigma yield, while failure of brittle material is by fracture where it breaks, and brittle material only have sigma U or sigma ULT, which is the ultimate stress. Criteria for failure is difficult to establish for components subjected to multi-axial stresses. So normally the manual calculation will do for simple 2D stress conditions, but for more complex components, we will need to use the finite element analysis approach to determine the principal stresses. Theories of failures used to determine allowable stresses stated in many design codes. So if you work in industry, most industry will have its own design codes. And these design codes are normally developed based on experiences in the industry, and also they are based on certain theories of failures, normally one of the four theories of failures. Okay. However, no single theory can be used for a material all the time due to effect of temperature. When temperature changes, material property changes. Rate of loading. When the rate of loading changes, material properties also might change. Chemical environment. When there's corrosive chemical or chemicals that react with the materials in the component, then it will also change properties of the material. And finally, production method. So production processes will change material properties. Therefore, in using theories of failures, although we say we know the material, but we have to check whether it has, in its use, there are temperature effect, significant temperature change, whether there are significant rate of loading, very high rate of loading, impact, things like that. Whether there are chemical environment where it's being used, and also production method. And the theories are based on knowing principal stresses. Okay, that's why we discuss this after stress and strain transformation. So we need to know principal stresses, and these principal stresses need to be known at the largest stress component, meaning critical points where you have very large stresses, especially if you have stress concentration. The first theory for ductile material is the maximum shear stress theory, or also called the Tresca yield criterion. Normally we call it Tresca. Now, the theory is based on yielding in ductile materials, which are usually caused by slipping along crystal contact planes, right? And these crystal contact planes are slipping due to shear stresses. And when you have uniaxial loading, the shear are maximum at 45 degrees to the loading direction. Therefore, we'll find lines of slipping of the crystals at 45 degrees. And we can note, or we can observe these lines if we do a tensile test on a specimen of metals, usually aluminum alloy or even steel. If we polish the surface, then we can see lines which are called Ludus lines. Okay, Ludus is the name of the person who first observed this phenomenon. For element under uniaxial yield stress, sigma yield, the shear stress is at 45 degrees and the maximum shear stress is sigma yield over 2. That is the maximum shear stress under uniaxial loading. So if we draw the Mohr circle, we'll find that we have sigma 1 on the right and sigma 2 is 0 because the stress element do not have stresses on this plane. So this is 0. Now you might ask, why is it called normally sigma x, but you can also call it sigma y, depending on direction of this element is drawn, right? But normally we take the axial direction as x, so you can call that x. But what is interest of for us is sigma 1 and sigma 2. So we observe that when it is under tensile, sigma 1 is maximum, sigma 2 is 0. When it's under compression, then it goes on the left and sigma 2 now becomes the largest value, magnitude, although it's compressive, and sigma 1 becomes 0. Okay. So if we draw the stress element for maximum shear stress, we'll find that the maximum shear stress is sigma yield over 2. And the average normal stress is also sigma yield over 2. Henry Tresca says that yielding begins when the absolute maximum shear stress in the material reaches the shear stress that causes the same material to yield under simple tension test. In simple words is shown in this equation here. When tau absolute maximum equals to sigma yield over 2, then the material starts to yield. Or if it exceeds, then it will certainly fail. So we have two conditions for plane stress. One is when we have sigma 1 and sigma 2 having the same signs, both positive or both negative. If both are positive, then sigma 1 equals sigma yield is the limit. That means when the magnitude of sigma 1 reaches sigma yield, then it starts to yield or fail. If both are negative, then we take sigma 2 as the larger value. So the magnitude of sigma 2 equals to sigma yield, then we will say it will fail. So this is when they are both negative, right? Both negative. And this is when they are both positive. Okay? But if they have opposite signs, this is positive and this is negative. Sigma 1 is positive, sigma 2 is negative. Then we will use this equation here, which says that when the diameter of Mohr circle, remember, diameter of the Mohr circle is equal to sigma yield, then it will fail. Sigma 1 minus sigma 2, and sigma 2 is negative, so it gets larger. Okay, so it becomes the diameter, because Mohr circle, when it's one positive, one negative, that's sigma and that's tau, right? Sigma 1, sigma 2. Sigma 2 is negative, we have 0 there. So this is negative, this is positive. So sigma 1 minus sigma 2, you will get the diameter for the circle, right? Now, if you have sigma 1 and sigma 2, what we do then is we plot on a graph of sigma 1 against sigma 2. Okay, the horizontal axis is sigma 1, vertical axis is sigma 2. And we plot location of the yield stresses. So in most ductile material, they have the same yield stress in tension and compression. Okay, so if we plot, then we have this blue shape here. And how we use that is, if we take sigma 1 and sigma 2 and plot it on this graph, if they are within the blue region, both of them, then they are safe. If one of them reaches the boundary or even exceeds the boundary, then we assume that the component fails. The second theory is called the maximum distortion energy theory. Some we use Huber or von Mises and Henke, but the common name that is used is von Mises. Okay. This is a common theory normally used, especially in finite element analysis. If you click to find the von Mises stresses, this is what is done. Okay, it compares the von Mises, the principal stresses with the von Mises theory. So the von Mises or maximum distortion energy theory says deformed materials tend to store the energy internally throughout its volume. That's the work done. Okay, so when we do work on a material by deforming it, it stores the work done or the energy inside the volume. So we have energy per unit volume is called strain energy density, and for uniaxial stress, the strain energy density is equal to half sigma epsilon, or half stress times strain. This comes from our graph of stress strain, right? If we have a straight line, then the energy is equal to the area under the graph. So it's half stress times strain. For triaxial principal stresses, we have U is equal to half sigma 1 sigma strain 1 plus half sigma 2 epsilon 2 plus half strain 3 stress 3 epsilon 3. This is for triaxial stress. If you apply Hooke's law for the linear elastic material, the strain energy density equation becomes this long equation here, right? And that is for triaxial stress state. But normally, we discuss or we do analysis on plane stress. Now, Huber does experiments, and from the experiments he did, he found that yielding occurs when the distortion energy per unit volume equals or exceeds. So if it equals, then it's considered to have failed. If it exceeds, then it's worse, right? If it equals the distortion energy per unit volume of the same material under simple tension test, then he says it fails because yielding starts to occur. So the equation up here can be rewritten as this equation here, right? And for plane stress, sigma 3 is 0. Therefore, the failure criterion then becomes this equation here. Strain 1 squared minus strain 1, strain 2, stress 1 squared minus stress 1, stress 2 plus stress 2 squared is equal to sigma yield square. Okay, again, we have sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square is equal to sigma yield square. And that is the criteria. If we plot this equation here, this equation is an equation for an ellipse. So if we plot on a graph of sigma 1 versus sigma 2, we'll get this blue ellipse here with the boundary on the principal axis is sigma yield. So we have sigma yield on all four axes. On all four locations on the two axes. So if we plot our principal stresses, sigma 1 and sigma 2, if they are both within the blue boundary, then they pass or they do not yield. If one of the principal stresses reaches the boundary or exceeds the boundary, then we say that the component fails due to yielding. Now, if we compare both the maximum shear stress theory and maximum distortion energy theory, Tresca and von Mises, they give the same result when the principal stresses are equal, i.e. sigma 1 is equal to sigma 2 is equal to sigma yield, or when one principal stress is 0 and the other is sigma yield. So we plot them both and we can superimpose them to have this diagram on the right. Now, this diagram on the right here shows that the Tresca theorem or maximum shear stress theory is more conservative. It is more rigid, okay, compared to von Mises, because for von Mises we have these small areas here which allows a larger stress to be applied to the material before it fails. Okay, so it says here under pure shear condition, torsion for example, pure torsion, then we can find that the maximum distortion energy theory is 15% more accurate than the maximum shear stress theory. So that is why we find that a lot of work or a lot of the code of practices are based on the von Mises theory. Okay, the von Mises is more accurate and is not as rigid as Tresca. We look at an example here. The steel pipe shown has an inner diameter of 60 millimeters and outer diameter of 80 millimeters. So we have a thickness of 10. If it is subjected to a torsional moment of 8 kilonewton meter and a bending moment of 3.5 kilonewton meters, determine if these loadings cause failure as defined by maximum distortion energy theory. The yield stress, given is 250 megapascal. So in this case, we need to find the critical location. So we have two conditions. One is torsion, okay? The other one is bending. So this is due to torsion and this is due to bending, right? So due to torsion, we have the maximum shear stress due to torsion occurs on the outer surface of the tube. And from our equation, tau A or B, they have the same value, is equal to T C over J, where as usual T is the top, C is the furthest distance from the centroid. In this case is R max or the outer radius, and J is the polar second moment of area of the cross section for the tube. We will get tau A is 116 megapascal. For bending, we know that the maximum bending stress will be at A or at B. Okay, so sigma A is mc over I, and we will get 101.9 megapascal. So now we take a stress element at the top, at A, because there is where we have both at the maximum value, both the shear and the axial loading, except that for bending will give you compression. Now for ductile material, it doesn't matter because we say that the yield stress under tension and compression, they are both the same. Okay. So if we do an analysis on this stress element, we'll find that the average normal stress will be minus 50.9. Okay, we can then use the values for sigma y and tau xy to plot Mohr circle. We can find the location of C from sigma average and the point A from sigma y and tau xy, which is negative. Okay, so we have point A, and from the Mohr circle we can find sigma 1 and sigma 2. Okay, we are not interested in the exact location of the planes and so on, because what we want is just the value of sigma 1 and sigma 2. So we want these values here. So from Mohr circle analysis, we can find sigma 1 is 76.2 megapascal and sigma 2 is negative 178 megapascal. So from von Mises or maximum distortion energy theorem, we have this equation here. Sigma 1 squared is minus sigma 1 sigma 2 plus sigma 2 squared should be less than sigma yield squared. If it is equal, then it will start to yield, so it will fail, right? So that is the limiting value. So we put in all the values for sigma 1 and sigma 2, and we check whether it is really smaller than sigma yield square. So from our calculation, this is from the textbook I take here. Now this on the right here is a separate statement, okay? If you calculate everything on the left, we will get the value is 51,100. Whereas sigma yield square is 62,500. Therefore, the value on the left is actually smaller than value on the right. Therefore, it is okay. It does not fail according to von Mises or maximum distortion energy theory.